Hello everybody. I would like to introduce our initiatives about predictive modeling approach for the COVID-19 propagation in France. This is a work made by Jürgen Reingruber, Andrea Papal and myself. We are from the group of computational biology, applied mathematics, data modeling, predictive medicine from École Normale Supérieure in Paris, France. So this presentation is organized as followed. I would like first to present the public data on which we worked, the mask and social distancing, and the hypothesis we've made to evaluate their impact on the evolution of the pandemic. Then I'll discuss the multiscale model and its tedious calibration that we've made, simulation result, and main conclusion of our simulations. First of all, public data. So the country, France, has been basically divided into two parts. The first part consists on the first five most infected regions compared to the other part here in gray. And as you can see, for the number of hospitalized, we have 23,000 compared to 90,000 for the five region. And as you can see here on this time evolution of the comparison between the five regions that I will describe in the next slide and France, you see a very similar parallel evolution. And so in mid-April, what we have used for this focus on five regions was the hospitalization number. We had 28,000 for the entire country versus 23,000 for five regions, which represent a ratio of 0.8, although the population for these five regions is 36.7 million. Versus 67 for the entire country, which is a ratio of about half. So basically half of the population concentrate about 80% of the cases. All our data came from a public website, Santé Publique France. So the five regions that we're interested in are the Île-de-France, Grand Est, Auvergne-Rhône-Alpes, Provence-Alpes-Côte d'Azur, and Hauts-de-France. So to better analyze the data from these five regions, we decided also to subdivide the age group into five: 0 to 24, group 1, 25 to 49, group 2, 50 to 60 to 59, group 3, 60 to 69, group 4, and over 70, group 5. And we have plotted here public data about hospitalization per group, the intensive care unit per group, the return home, the cumulative, and the death cumulative. So this is for France, and this is for the five regions. And to monitor the differences between the five regions and France, we decided to divide the cases for France divided by the cases for the five regions. And by doing so, what you observe is that this ratio was almost constant for the four parameters that we studied here. And so when we collect data, we use this ratio to extrapolate and better calibrate our model. So the construction of the multiscale rate model. So the present model differs from the classical SIR model and their extensions. It turned out that it is flexible because it accounts for several time scales that I will explain. And this model can account for changes in decision occurring in hospitals, changes in decision, for example, when people have to stay longer in ICU, and which is a general decision. This impact has a large impact on the evolution of the different parameters, such as the number of people in ICU and hospitalized. And the present model can be updated in real time and can be used to really predict in an exponential phase situation how to change policy in order to keep control about the evolution of the pandemic so that we don't get ICU and hospitalized saturated. So the model construction is made for the 5 groups. Then what we are doing is we introduce the notion of category, such that a person that is infected, hospitalized, in ICU or recovered, each of these corresponds to a category. And the subtlety of the model is not only to have the time evolution per day, but the time after infection. We have a specific timer to measure how long a person stay infected, how long a person stay in hospital, how long the person stay in ICU or recovered. So we can measure time after infection, and in addition we can measure the time spent in each category. And this allowed for, when we will do the calibration, to have a model which is very precise. So I'm not going to describe here the specific mathematical modeling part. It will be the subject of another talk, but basically, if you think about the number of susceptible in the group of age k, 1 to 5, at time n+1 equals what happened at the susceptible at time n minus the number of people that are infected. And then we wrote equation for this infected. And so again, S and K represent the number of susceptible at time n in group K. And then what we used here for the number of infected, so we look at the number of people belonging to group K from a given category. For example, the person has just been infected. And then we look at the number of days, n, at date m, where after the person has been infected, and at the day l in the infectious category j. So we can then use this 3 time scale, which corresponds to convolution in the differential equation. So to account also for the frequency of contact between these 5 groups, we use a specific contact matrix that was published in this very nice and documented paper published in PLOS ONE by this group, where basically you can see here the age group and the contact they made with a different age group. For example, the large peak here corresponds to all the frequency and contact that young people are making between themselves, and the second peak here corresponds to the contact they made with the more older people. And so you can use this to account for the contact matrix in the population across group age. And so we reduce here this to a 5 by 5 matrix according to the group decomposition. And this we use this matrix before confinement. During confinement, we had to adjust this matrix to account for specific interaction during confinement, where a lot of classical interactions are removed because they occur so often at school, in public places, or in office places. Now, to motivate our study, I just would like to introduce briefly the effect of mask. So, in a recent study published in this New England Journal of Medicine, this group, using a laser light scattering, have monitored the oral fluid droplets after when somebody is speaking. So you can see here on the left all of these droplets, these microparticles that are generated. The same situation is with the mask. So the person is still talking, but then all of these large droplets do not appear. So mask reduces immediately, drastically projections. But as we are going to see, those large projections are not those that are the most sensitive for the propagation of the pandemic. So wearing mask can also drastically affect the diffusion of the disease. So this is a study that we did 1 month ago, where by plotting the number of new infected people as a function of time for different countries, France, which used containment, Hong Kong with just mask, and Czech Republic with mask and containment. So you can see here how this evolution is contained, especially compared to Hong Kong, where containment was not mandatory. So this suggests that masks can stabilize the growth of the pandemic, similar to confinement. And finally, we use another study about the propagation of the pandemic using masks. And in the studies, they look specifically at the effect of coarse versus fine particles. So fine is less than 5 microns, coarse is larger than 5 microns. And what is interesting is that they show that the fine particles contain about 10 times fold more viral particles than did coarse particles. So those are the ones that are the most important. They move by diffusion, they can stay in the air, and they can lead to these high contaminations. So one of the conclusions of this study is that surgical masks can reduce viral particle numbers in the fine fraction by about 2.8 fold. For the coarse fraction, for the coarse particle, it's about 25 folds, and on an overall of 3.4. So we are going to use this information to hypothesize that masks can reduce. They could reduce the R0, which is the rate of the number of people that an infected person can infect during the time of infection of this person. And we're going to use two numbers, 2.5 and 3. So we are going to assume that wearing masks can reduce R0 by 2.5 and 3, and see what would be the consequence on this after deconfinement. So to calibrate the model, we use for the different countries before confinement, what was the rate? And the rate was estimated by this factor B. So f of t was exponential bt with b around 0.2. And our first initial calibration of the model leads to an estimation for our parameter of 0.18 that has to be compared to 0.2. And then we refine our model, and this is now what I'm going to briefly show to you, how accurate can be the calibration. So in this first figure on the left, where we have the number of hospitalized per day, you can see here the data versus the simulation, and how good is the model after we change the parameter of the model. And so not only we can do that for the total number of hospitalized, but also for the number of people hospitalized per group of the different group age. And I remind you here, what are these group age from 1 to 5. Then not only we have the number of hospitalized, but you can also see how the model performed to the number of changes in hospitalization. The number of people in ICU, in intensive care unit. Again, the continuous curve is the model, and the dotted the points here corresponds to the data. Then we have here the total number of people in ICU, the change in ICU per day, and the change in ICU per group. Then to further calibrate the model on the fluxes, that is how many people enter in, for example, ICU or hospitalized. So we show here the effect on the cumulative death. So before this was here the death as a function of day, and again you can see how good the model does in the taking into account the different group. Number of cumulative deaths, the number of recovered in hospitals, the number of recovered hospitals, the total number here, and the total number here per group. So based on this very satisfying calibration of the model, we decided to investigate various scenarios. So first of all, suppose that in France there is no deconfinement, and we ran the simulations for 300 days. And you see that after 300 days, we have the proportion of infected that saturate at 14%, although you see a large disparity of the number of infection per group. So you can see, for example, that group 5 has less than 3%, while group 1, which corresponds to the population less than 25, is around 16%. And the most, the red is the group 2, which is the group from 25 to 50, and group 1 here is less than 25 years old. So you see that you have a small fraction of infected people, a large variability among age groups. Later fluctuation can recreate quickly a pandemic because there is no collective immunity acquired here. So now what we did is we just ran the simulation with the monitoring of the parameter I showed you previously after 300 days for the number of hospitalized per group. And you see that in all these cases, the ICU is not saturated, neither the hospital, and everything is terminated here after 200, and we didn't include here any effect of the noise that could lead suddenly to, of course, a regeneration of the pandemic. Then this is a scenario had the French population not have been confined, and the simulation shows, so this is here where we are after confinement day. So this is the data, and had we not been confined, you can see here this huge peak where if we go directly here, the ICU would have been completely saturated with a need of hospitalization of 350,000 at the peak, with a number of deaths at the peak of 12,000. So I'm not going to go over all of this detail, but the main conclusion here is about 250,000 deaths in the 5 regions, 80% of people infected, and a full saturation of the ICU for 50 days. Then the next scenario we decided to investigate is what happens if we have deconfinement, but with the same rules during the period of deconfinement as the one before confinement. And so you can see here the peak that we have seen in April, and then short after deconfinement you can see the genesis of a huge large peak, which is about 6 times the one that we have observed in April. The consequence of this, if we go directly here to ICU, would be a saturation of ICU for 50 days with a large number of deaths and a number of hospitalization of the peak of 320,000. Here would be the cumulative deaths, about 220 deaths for the 5 regions, where you can see here the beginning and then suddenly the huge rise in the number of cumulative deaths. Then we decided, based on the inspiration that we got and the hypothesis we made on the information from the mask effect on the R0, we decided to study 3 cases. What would happen if R0 would be maintained at R0 divided by 3? R0 is the initial contamination before confinement. R0 divided by 2.5 and R0 divided by 2. We hypothesize that if the mask can reduce the number of refined particles by a factor of 2.8, then it could possibly lead to an R0 which is in this range. That's why we studied this 2.5 and 3. And also we see what happens if we lose control to 2. So if we look at the number of infected fraction, as you can see here, for a full deconfinement, we lose completely control. And so the round circles here show where we are today. So if we stay confined, this is a dark curve, and again, everything is under control. R0 divided by 3 is still under control. R0 divided by 2.5, you can start to see here an increase in the number of people infected. And then we have here the case of R0 divided by 2, which leads here to a sudden large increase of the fraction of people infected. And the consequence here, you can see on the new number of infected, in the case of hospitalization, we can see here the full deconfinement leads to this huge second peak. With R0 divided by 2, we still have a second peak, which is a bit larger than what I have seen in the first peak in April. While if you are between R0 divided by 3 and 2.5, the peak is smaller. So we are still, and as you can see here in the case of ICU, you are still under control for ICU. While if we drift to 2, you can see that in green you lose control and the ICU start to be saturated. And this leads to different accumulated deaths that you can see here with full deconfinement, R0 divided by 2, R0 divided by 2.5 and 2. And in summary, with these different numbers, you can see what's the change in the number of deaths in hospitals: 21,000, 35,000 and 70,000. I do not account it here for people, the elderly people that are placed in special retirement houses. And this led to 16%, 30% and 50% of infection. So the main conclusion of the model: at the time of deconfinement, for the French population, 13% of the 5 most critical regions would be infected. And we use the ratio that I discussed at the beginning to estimate that this would correspond to 4.6 million of people infected by Monday, May 11th. The scenario of deconfinement, 240 days after confinement, if the population is not deconfined, 40% of the people will be infected, but the pandemic could persist at low noise. Scenario of no confinement, if there was no confinement, this would have led to a drastic number of deaths, 12,000 of deaths at the peak, a total of 250 deaths in the 5 regions, which would probably be equivalent to 450,000 around the entire country. 87 of the population would have been infected, and ICU would have been completely saturated for 15 days. And I explained to you what would have happened for the different age group, specifically, for example, for the group with the age larger than 70, 40% would have been infected, which represent 160 total deaths for these 5 regions. So the deconfinement with no restriction would lead to a large second peak, as expected, with 220,000 deaths for the 5 regions after 200 days. ICU will be saturated with a need of 320,000 hospitalization at the peak. The deconfinement with restriction, so when R0 is divided by 3, no second peak, the pandemic is under control after 300 days. The proportion of the infected population tends to 18%. And the total number of deaths for these 5 regions is about 20,000 in hospitals. If we move to 2.5, then instead of 18, we have 30% of the population infected in 30 days, with an increasing slope, and cumulative deaths around 35,000. So basically, R0 should be maintained between 2.5 and 3. So this is quite tricky, because we are in an exponential phase where any fluctuation is largely likely to be amplified. And so there is really a need for a constant monitoring. This phase is very sensitive to this social interaction. And we have shown here that possibly with wearing masks would have exactly this effect of maintaining the R0 between 2.5 and 3. This has to be checked to make sure that this could happen. And if the present model give a prediction, the prediction that this model give is about a number of infected people that should be less than hundreds of thousands per day. So having 100,000 tests per day should be important, and have to be, this number of tests has to be integrated in the modeling to see exactly how they could be used to change a policy if needed. If we see that R0 suddenly, instead of being divided by a number between 2.5 and 3, is divided by a number less than 2.5, where we risk another a possible saturation of ICU. I would like to thank Professor Dan Longra for discussion. The model can be adjusted here for any countries, all of the French region, and we'll be happy to share. This model is not easy to calibrate. We need to train somebody if there is a need. The software can be used to estimate R0 and predict the changes in the next few weeks. The software are developed in MATLAB, Mathematica, and Maple. And we thank here the public sources from the French government, Geodes and DataGov, where we use the data for this study. And I would like to thank you for your attention. Thanks.